Hi everyone, this is Mrs. G, and today we're going to be modeling with exponential functions. But first, please pause the video and give this warm-up a try. All right, go ahead and check your work here. So this is something we talked about in the first semester. So remember, if your data has a common difference for the x values, you can look for a pattern in the change in y values. So for part A, you'll notice that if you check for a common difference, there isn't one. So it's +9, then +7, +5, +3, +1. But remember, then we're going to look for a pattern with the differences. And you'll see that here, each time we're subtracting 2. So this is what's called a common second difference, and that indicates a quadratic equation. And then for part B, we do have that common difference for x and a common difference for the y's every time we're subtracting 2. And so that's a common first difference, which represents linear data. So today we are going to be modeling with exponential functions. So the first thing we need to learn is how to identify exponential data. So the first thing we look for is, again, that common difference in the x values. And if you notice that, then you're going to look for a pattern in the y values. But this time, instead of looking for adding or subtracting by the same thing, we're going to be looking for what's called a common ratio. So what is a common ratio? Well, if you look below here, we do have that common difference in x values. We add 1 each time. Look at the y value patterns. From 1/2 to 1, from 1 to 2, from 2 to 4, you'll notice that each time we're multiplying by 2. That is what we call a common ratio. So a common ratio is when you multiply by the same value in each step. So again, rather than looking for a common difference or even a common second difference, we are now looking for a common ratio. And that value can be bigger than 1, or it could be a fraction less than 1, or it could be a fraction bigger than 1. So it doesn't have to be a whole number. If your numbers are getting smaller, then your common ratio could be a fraction that is less than 1. All right, so let's look at these two sets of data and determine if we would model this with an exponential function. So for the first one, there is a common difference for the x values. Let's see what's going on with the y values. So here I have -3, -3, -3. So this is not exponential. And again, as we saw in the warm-up, this is linear, because it has a common difference every time we are subtracting 3. So this we would not model with an exponential function. But if you look at this second one, we do have that common change in x, so +2, +2, +2. Let's see what's going on here. To go from 27 to 9, we're actually, well, we could say we're subtracting, but we could also say we're dividing by 3. 9 to 3, we're dividing by 3. 3 to 1, we're dividing by 3. But each time we're going to want to phrase it as if we're multiplying. So instead of saying dividing by 3, let's say we're multiplying by 1/3. So here you can see that we have a common ratio of 1/3. So this is exponential. And our justification would be because there is a common ratio of 1/3. So again, that new word that we're focusing on this time is ratio, meaning we're multiplying by the same number each time rather than adding the same number each time. All right, go ahead and pause the video and give this one a try on your own. All right, so here you'll see that there's no common difference, but in this case there is a common ratio of 3 because each time we are multiplying our y value by 3 to get to the next term. So now that we know how to recognize exponential data, we're going to practice writing an exponential function in this form, y equals a times b to the power of x, when we are given 2 points of the function. So here, we are going to need to solve for both a and b. B is the base of our exponential term, and a is that coefficient that we see with any type of function we're modeling that would make it specific to this function rather than a general exponential function. So to do this, since we're trying to find two variables, we're actually going to have to set up a system of two equations. So I'm going to do that by taking those two values that we're given, and we're going to substitute them for x and y. So if I substitute 1, 6 into this equation, we get 6 equals a times b to the power of 1. And if I substitute 354 into this equation, we get 54 equals a times b to the power of 3. So here, what I can do is I can isolate one of these variables and I can substitute it into the other equation. So here, let's try to solve for a. So if I divide both sides by b, we get a equals 6 over b. So this is an expression that we can then substitute into our second equation. So I'm going to replace a with 6 over b. So we have 54 equals 6 over b times b cubed. And if we clean that up a little bit, well, we have b cubed divided by b, which is b squared. So that gives us 6b squared. If I divide both sides by 6, we have 9 equals b squared. So b is going to be the plus or minus square root of 9. So b would be plus or minus 3. However, we know for an exponential function, this is just part of the definition, the base must be positive and cannot be 1. So our b value is simply going to be positive 3. So once we have one of our variables, we've solved for b. Now all I need to do is substitute it back up here to solve for a. So we have a equals 6 over b, which is 3. So that means a is 2. So now we have both of the variables we need to make our function. So if our function is in this form, ab to the power of x, we would have y equals 2 times 3 to the power of x. And this would be our exponential model. All right, go ahead and pause the video and see if you can give this one a try on your own. All right, go ahead and check your work here. So you can see here's my two initial equations that I got by substituting the coordinates into this function. And then I isolated a, and I substituted that into my second equation. So you can see I replaced a with 10 over b. And that allowed me to solve for b. So we get b is positive 2. Remember, the base of your exponential term must be positive. Then I can plug that back into this expression. So you can see I replaced b with 2, and that allows me to solve for a. So then I plug a and b back into this general form, and here's my exponential model. All right, let's try one last example together. So this says the table below shows the number in thousands, that is important, in thousands of people who visit Machu Picchu X years after 1990. Write a function that models this data. So here we have a set of more real life data. So when we're modeling real life data, it's not always going to be a perfect fit. So if I check for a common ratio, we might not find an exact common ratio, but it might be really close. So one way we can check to see if a set of real world data is exponential is by plotting it on a scatter plot and seeing if it kind of makes that general exponential shape. So let's take a moment and let's plot these coordinates on the scatter plot that we're given. We are just going to have to estimate for some of these. Like 0, 1, 50 is going to be somewhere around here. And then we have 4, 2, 10, 8, 3, 60. And then we have 12, 4, 70, 16, 700. Then 20, 700 also. And then 24, 1150. and 28, 1580. So if you look at our data, we can see that it does follow that general trend of an exponential function. It wouldn't be a perfect fit. Like I can't draw an exponential function that will go perfectly through all these points, but I can see that there is that general trend. It makes the general shape, so I can say, all right, we can model this with an exponential function. So then from here, what you're going to do is you're going to select 2 points from your data. You can just make sure in your scatter plot, make sure you're not picking a point that is a clear outlier. I think any of these points would be just fine. But let's do 0, 150, and let's do, I don't know, 20, 700. Okay, so you can pick any 2 points that look right to you. Those are the 2 that I'm going to use. So we have 0, 150, and 20, 700. So we're going to do that same process that we did before. We're going to use this model, y equals ab to the power of x, and we're going to see if we can make a system of equations to solve for a and b. So if I substitute 0, 150, I get 150 equals a times b to the power of 0. And here I would get 700 equals a times b to the power of 20. So this is actually a nice point to pick because b to the power of 0 is 1. So with this one, we can actually solve for a completely. I could take that and I can plug it into my second equation. Times b to the power of 20. So I can divide both sides by 150. And here, I know this is going to seem a little strange, but if I have something to the power of 20, the way I undo that is by taking the 20th root. So I have the 20th root of 70 or 700 over 150. Which is something that, in this case, it's probably better for us to plug this into our calculator to get a decimal approximation. So if you plug that into your calculator, you get approximately 1.08 for your b value. So that means that our model would be y equals 150 times 1.08 to the power of x. And then we could use this model. The purpose of doing this is to use this model to make predictions about years that we don't have data or even future years. We could make a prediction about how many people would visit Machu Picchu in the year 2050 using this model. So that's why modeling is useful. It helps us make predictions, or it helps us fill in data that we may not have. All right, here's one last example for you to try on your own. So start by making your scatter plot to see if it looks exponential, and then pick any 2 points that you want. Maybe just for consistency, let's pick this point and maybe this point. So we will end up with the same answer. All right, go ahead and check your work here. So by plotting the points, you can see that it does, this data does follow a general exponential trend. So using the 2 points that we pre-selected, I made these 2 equations. And this allowed me to solve for a, which I substituted right here. And then I solved for b, and I plugged this into my calculator to get this decimal approximation for b. And then from there, I have my answer. So 487 times 1.07 to the power of x. Now, of course, if you picked a different 2 set of points, maybe your answer would be slightly different, but it should be very, very close. All right, that is all for today's video. Thank you so much for watching.